Presented by Caltech.
So we started talking about coupled oscillators. So I drew up a little recap of where we are. We're considering two pendulums with a spring between them. They can do whatever they do. And we wrote down the equations of motion, which we can write in this matrix form like that. But we still need to solve it. We still need to solve for the motion. But before we do that, let's get a feeling for what we think the actual behavior really is going to be, because I have some toys up here that we can look at and maybe get an idea. So this, here I have two pendulums coupled with a spring. It's almost identical to that. There are additional springs on each end, so it's not quite the same. We'd have to modify our equations a little bit, but it's almost completely the same as far as the basic ideas. So I can, for example, start one of these moving and see what happens. Pretty soon the other one starts moving and the first one slows down. And then the first one starts moving again, the second one slows down. So they're clearly coupled, the motion's clearly coupled to each other, like we saw in some of the examples last week. It just sloshes back and forth. Are there other things that we can do? So one of the questions we may want to ask is, are there motions that are really steady state, that don't somehow change as a function of time, where the amplitudes are constant and everything goes in phase? Well, we can guess on this system. It's a simple enough system. We can guess what they might be. If I make both pendulums swing together such that the spring doesn't change its length. Okay, I have the outside spring, but they're more or less pushing the same. Maybe that's a way that would work. Let's try it. Bring them about the same amount. So I can't get things perfect, but more or less they're going together. And I'll just keep doing that. And so it's not sloshing back and forth. There's something special about what I did. So there are 2 degrees of freedom here. And you might expect, and we'll get some more intuition for this as we go along, you might expect that that's not the only kind of steady state motion that you might have. Once we look at the matrices, that'll become more obvious, but maybe there's another mode that you can think of where they both have the same amplitude and the amplitude stays constant, and that doesn't change. Well, what if I do this? That looks pretty symmetric, so that looks like a good candidate. And indeed, it does look like they stay in that state. Now get a feeling for what the frequency of this is. Okay, 1, 2, 3, 4. Let's try the other mode again. One, 2, 3, 4, 5. I don't know if you can really tell or not, but I'm counting slower for this mode than I did in the other mode. So there are 2 different characteristic frequencies of these special modes. These are called the normal modes of the system. They're special in the sense that the motion is constant. Everything stays at a constant kind of amplitude, as opposed to doing that, where the motion sloshes back and forth. And actually, I've excited both modes here. So I can describe what's going on here as, in fact, a superposition of the 2 special modes. And we'll work out the mathematics on that. So I can illustrate the same thing, perhaps in a little more detail with this. So it's no longer pendulums, it's just masses on springs. So I can, so the motion sloshes back and forth between the two, just like it did on the pendulums. I can try to find the special modes by driving this. It's just like when we had a single mass on the spring, I can look for resonances. The amplitude. So when I hit a resonance, that will be one of the special modes. So here we guess that the special modes are going to be like this. So you can see 1, 2, 3, 4. And you can guess the other one from the example we just did. 1, 2, 3, 4, 5, 6, 7, 8. It's a higher frequency. Here, figure out why it's a higher frequency. In this mode, this spring is not doing anything. It's just a constant length. In this mode, this spring is doing a lot. You're getting this spring constant added into your calculation of the frequency. All right, let's see if we can see what happens. So those are the two modes I expect to see at resonance. So I can try driving these things. So I'm driving this at a fairly low frequency now, and so it's a little hard to tell when you're below frequency, below resonance like this, but I am below resonance. So I actually am pushing this, and it's not quite going in phase, and the amplitude is small. If I crank it up and go a little faster and get to something close to resonance, I should get the low frequency mode. So they look like they're moving pretty much in phase now. Maybe the amplitude isn't spectacular, but it's bigger than it was before anyway. So that's the lowest frequency resonance. I can go up a little farther. You can see things are starting to get a little they're not quite going together anymore. Yeah, this one's going a little faster, and it's trying to catch up, and it's not keeping up. It's even more pronounced as I go up. That middle spring is starting to stretch and compress. Now you can really see. It's no longer doing this, it's doing this. This is the second resonance, roughly. It's taking some time to get up to speed, but that's the second resonance. Just like these, all right? No difference, really. A little bit of, the matrix that we write down is going to be a little bit different. It doesn't involve gravity. But it's the same, otherwise the same mathematics. So when we have these two special frequencies and they're both being excited, the motion has two frequencies to it. So the motion gets kind of complicated. But basically we're adding two sine waves together, and we're going to get some kind of beating effect between them. And we can illustrate that perhaps most conveniently nothing's going on there, that's just noise. But I'm going to feed in two signals. So I have the green signal is a 1 kilohertz signal. The red, ignore for the time being. The blue signal is 1 kilohertz plus 0.6. So the difference is 0.6 of a hertz. So the red graph is the difference between the other two traces. Now you should be able to hear things on the speakers. You hear about a 1 kilohertz wave. Can you also hear a beating? That beating should be coming at 0.6 hertz roughly, or something like that. Okay. I can maybe change. Now I've got 1,002.1 compared with 1,000. You can see the beating now on the red. It's going boom, 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 boom. So you can correlate that with the speaker maybe, if your ear is really good, your eye is really good. Let's just see what this looks like if I go to a really expanded, compressed scale. So now I can see that red is really doing the beats between the two. So that's the superposition of these two special waves at two different frequencies. Well, they're not so special there, I dialed them in, but the same thing happens when we have coupled oscillators that are being driven at multiple frequencies at once. I better turn that off or it'll drive you crazy. I still hear it. I hope you don't. That should be better. Okay. So we've done two coupled oscillators now in terms of looking at what they do. There's nothing to keep us from having more oscillators coupled together. I could add additional balls. I'll probably do that next week. I'll put 6 of them together and we'll try to look for the normal modes. But I have something here called a wave machine, which is basically just a bunch of coupled oscillators. So each one of these is an independent degree of freedom, except that they're linked together with a wire, so it's like a torsional spring. So I can excite that and hold this, and this just goes back and forth somehow. But if I excite this and let the coupling do its work, all these coupled oscillators are talking to each other. So there are about, I don't know, there are about 80 of these things. So I have 80 degrees of freedom. And as we'll learn, I have 80 degrees of freedom in a coupled oscillator like this, where they're all kind of identical oscillators, there are 80 normal modes. There's one normal mode where everything goes up and down at the same time. I can't do it quite because I don't have enough hands. There's another normal mode where this goes up, the alternating ones go up and down with respect to each other. So that's the lowest and the highest frequencies that we're going to have in this system. And as you saw, I'll anticipate the future. You saw it looks like a wave. It looks like there's some kind of motion going back and forth on this thing. So that's where we're going eventually with coupled oscillators, is we're going to couple together a whole bunch of them, eventually an infinite number, and we're going to be able to make waves, either traveling waves or standing waves, and we'll talk about that. So I have one more toy that I'd like to show you just for kicks. It's way over here in the corner. It's two pendulum. So there's a pendulum up here, a pendulum down here, except one pendulum is attached to the bottom of the other pendulum. Some kind of a compound pendulum. So for small motion, like we've been analyzing, it looks like we could probably solve that system. So we're talking about small motions in this course. Except what happens if I give it a large motion? Try to predict that. I could get even more extreme. Maybe. So the motion starts to look chaotic. And it's a mechanical system. It's in principle completely predictable, but it's very sensitive. What happens is very sensitive to my initial conditions. I mean, I can try to reset the same initial conditions I had the first time, something like that. But if you remember what it did the first time, it's probably not doing the same thing anymore. You know, it really has a mind of its own. So that would be an interesting system to analyze for chaotic motion of the two pendula for large motions. Small motions, of course, it looks perfectly plausible, perfectly reasonable from what perspective of everything we've done. So you can amuse yourself by trying to solve that for large motions, or even small motions. That would be fun too. Okay. Any questions about the toys? I want to solve this pendulum now. I want to figure out what the motion really looks like. So we've already kind of know what it's going to be. We know it's going to be a superposition of these two normal modes. These two normal modes have well-defined frequencies, and I can just write down what the answer is for those. But let's pretend that maybe it was a little more complicated and I can't quite write it down. So what do I have to do? I have to solve this equation of motion that's written in matrix form here. Unfortunately, it's a coupled differential equation. So I have to figure out how to deal with that. I can't just simply do it like I did the single oscillator. So there's M, the matrix M. The off-diagonal elements are what makes it coupled. It's a real symmetric matrix. So I know that I can diagonalize it with an orthogonal transformation, a rotation in 2 dimensions. So let's try to carry that out. and see what happens. So what do? We look for an orthogonal transformation. Call it O. It's orthogonal, so O is equal to O transpose. Sorry. O inverse is equal to O transpose, not O. Such that I have my x coordinate system with components xa and xb. So I want to find a new coordinate system such that in that new coordinate system, M is diagonal. M becomes a diagonal matrix. So we define new coordinates u1 and u2 that are related to x by an orthogonal transformation. U is just u1, u2, where x is equal to xa, xb. Okay. So what do we do to find O? Well, we have our differential equation. Let's apply the transformation to the differential equation and see what we get, because what we get when we apply it, we hope will give us a matrix that's going to be diagonal. So O times d squared by dt squared x plus mx equals 0. So we apply our transformation to the whole equation. O is a constant, okay? It's going to be a constant. We're going to look for a constant matrix that works. So I can put it inside the derivatives. And so what do I get when I get that? I get d squared by dt squared u1, u2. O times x is u1, u2. Plus O times m times x. But let me insert the identity in the middle here. That's O inverse OX. So this is just O times mx, but I've inserted the identity because what I get from here is just U. So let me write it as U1, U2. And what I get here is some matrix that I'll call D, because I want it to be diagonal. And I can write this as U1 double dot, U2 double dot. And that's all equal to 0. No. I get them all? No. A little better. Okay. Well, the whole point of this exercise is that D equals O M O inverse is diagonal. If I can find the transformation O, I haven't found it yet. If I can find the transformation O such that this is diagonal, then I've decoupled the motion in the U coordinate system. And then I can just, I've done those integrals before. I can directly get the equations of motion in U. And then I have to transform back to X. Let's see. So let's think a little bit about this. So I've got to find O that makes D diagonal, given M. start looking like thetas. Oh, you know, I'm never going to get this. Just not used to it. So we know that O transpose is equal to I. I just want to, I'm just belaboring this a little bit in case you haven't, or you've forgotten it from linear algebra. So that means that the determinant of O times O transpose is equal to 1. But that's just the determinant of O times the determinant of O transpose, which is the determinant of O. Yeah, okay. I'll never do it. Squared. Is that all right? Determinant of a product is a product of the determinants. And the determinant of the transpose is the determinant of the original matrix. So that says, so that is equal to 1. So therefore, determinant of O is equal to plus or minus 1. I could do either. Let's just keep our life simple and choose plus 1. I could just as well choose minus 1. What would that do? That would add an inversion in my coordinate transformation. But if I choose just plus 1, I just have a pure rotation. So minus 1 is what you call an improper rotation that has an inversion in it. Plus 1 has is a proper rotation. It's just a strict rotation. So 2 by 2 orthogonal matrix, the determinant plus 1. In 2 dimensions. Just a rotation in 2 dimensions. So that's just going to be O is equal to, I can write it as cos. See, now I have trouble. I'm going to have to be very careful how I write my thetas and my O's. Oh well. Minus sine theta, sine theta, cosine theta. I'm making progress. I just have to figure out what theta is to make D diagonal. Let's so I've got G over L and K over M showing up in my matrix M. I could just leave them that way, but I'm going to simplify my writing a little bit by defining alpha to be G over L and beta to be equal to K over M. And so if I do that, M looks a little simpler as just alpha plus beta minus beta alpha plus beta. So now we just have to multiply 3 matrices together. O inverse is O transpose, remember. So we already know what the inverse of that is. It's just the transverse and transpose, and you can just check and make sure, but you already know that. And so I'm not going to work out the, I'm just going to give you the answer here. Alpha plus beta plus 2 beta cosine theta sine theta. Let's see. minus beta times cosine squared theta minus sine squared theta minus beta times cosine squared theta minus sine squared theta, and then alpha plus beta minus 2 beta cosine theta sine theta. So you can, yeah. It's OM O inverse, but O inverse is O transpose. So I can write the transpose. I mean, otherwise I just have to figure out what O inverse is and plug it in. But I would find out that that matrix, the inverse, is in fact the transpose. So we're good. Okay. That's a diagonal matrix. Well, it doesn't look quite diagonal yet, but so now let's make it diagonal. We can pick theta. Well, that's the only thing we can pick here, and so that's what we have to do to make it diagonal. So this is diagonal if cosine squared theta is equal to sine squared theta. So the sine and the cosine are plus or minus each other. So this can happen if theta is, say, plus or minus pi over 4 up to addition of integers times 2 pi. So I might as well choose plus pi over 4. I could do it either way. I get the right answer either way. I might have a different sign convention somewhere. But let me choose whatever looks simplest, which to me is pi over 4. So therefore, sine theta equals cosine theta equals square root of 2 over 2. It's 45 degrees. Okay, now we're there. D is what? Okay, so alpha plus beta cosine theta times sine theta is just 2 over 4, 1/2, so it's just beta. Where did you know? That's nice. And I got rid of the diagonals, the off diagonals rather. And then we have alpha plus beta minus beta. So we have, if I plug in, the alpha is G over L, so go back to our physical quantities. G over L plus 2K over M. And G over L. That's it. We got the diagonal matrix. We could read off the frequencies just for the matrix now that we've got it. In a minute, we'll talk about eigenvalues and eigenvectors in a little bit. But okay, let's just keep going. Equations of motion. So we have an equation of motion. Let's separate out the two. U1 dot plus G over L plus 2K over M. U1 is equal to 0. I'm just using this. We use the diagonal matrix. And U2 plus G over L, the bottom part there, U2 is equal to 0. So this is our familiar simple harmonic oscillator. No damping, no driving. We can read off the frequencies here. So the natural frequency of this, so they're decoupled. They don't talk to each other. They're two independent, yeah. Sorry, I'm having trouble hearing you.
So we switched into U from X, like to using the rotation. Does that mean that when we look at the problem, the coordinate system is
Yeah, I've changed coordinate system. I've changed to U here. So these are what we might call normal coordinates, because I've decoupled the motion. Then I have to, if I want to go back to X, which I'll do, then we'll see what it means for X. So the natural frequency of this oscillator squared is just G over L plus 2K over M. The natural frequency of this oscillator is just G over L. So this one's a higher frequency than that one. This one doesn't involve K. So we guess that's probably the one that's going like this, where the spring is just neither compressing nor expanding. It's just staying the same length. It's not doing anything in the sense of there's no change in the energy in that spring. It's just constant force back and forth. So that we guess is this one. And the other one we guessed then must be this one, where the spring really is compressing and expanding. Okay, so we can maybe see this more clearly if we do transform back to X. So in terms of X sub A and X sub B, well, let's see. We have U1, U2 is equal to O XA, XB, square root of 2 over 2 times 1 minus 1, 1, 1. So that's our matrix, cosine and sine theta. XA, XB. So I multiply that out and I get XA minus XB and XA plus XB. So that's now the transformation, how you do the transformation of the components between the X coordinate system and the U coordinate system. So we have two non-coupled normal modes. U1 is proportional to XA minus XB, if I don't worry about the square root of 2 over 2. So what's that look like? It looks like And motion going back and forth. And because the spring is getting extended, that's the one with the higher frequency. U2 is proportional to XA plus XB. That's just the motion like that. The spring simply stays at equilibrium the whole time, so it doesn't enter into the frequency. It's just the gravity. So we've got a complete solution now. It wasn't that bad. We can now think about another way we can look at this. What have we done? We've really just found the eigenvectors and eigenvalues of our matrix M. We did it quite explicitly by going to a diagonal coordinate system and then reading it off. But the idea is that we solve this eigenvalue equation. M times some vector v is equal to lambda times v if v is an eigenvector. And lambda is the eigenvalue for that eigenvector. So this is an equation in our x coordinate system. And so what did we do? M times u1 is equal to m times 1 minus 1 up to multiplying by a square root of 2 over 2. Okay, I'm going to drop the square root of 2 over 2. I mean, of course, this is a homogeneous equation, so I don't need to worry about constants like that. So if I do that multiplication, do I still have m? Yes, but you'll have to look at through the board through it, but I'll have a g over L plus k over m minus k over m. Well, the minus k over m is times this minus sign, so I will have g over L plus k over m plus k over m. And then I will have a minus k over m minus g over L, because there's a minus in the off diagonals on m, minus k over m, where this minus comes from here. So what is that? That's g over L plus 2k over m times 1 minus 1. So that's an eigenvector. This is the eigenvalue, the square of the natural frequency. Do the same thing with U2. 1. It's equal to g over L plus k over m minus k over m. And then a minus k over m plus, so this becomes a plus because there's a plus sign here, g over L plus k over m equals, so the k over m's all cancel, g over L times 1, 1. Again, an eigenvector with eigenvalue g over L. So knowing this now, you can use whatever technology you have at your hands to find eigenvalues, and if you want, eigenvectors. If all you want to do is find the frequency, you could do something like solve m minus lambda I, that determinant is equal to 0, and that'll give you the frequencies. Without going through all these steps that I went through of finding the orthogonal transformation explicitly. All right. Well, I mean, if we have this coupled oscillator system, we can drive it, just like we did with the motor. So let's consider the forced coupled oscillator. So let's suppose we had a driving force. Our two masses on the spring, A and B, and we put a force on it, external force. So our equations of motion become x of A double dot. So it's the same equations of motion as we'd written down there, G over L XA plus K over M XA minus XB, except we've added a force on mass A. So this is equal to F. We've divided through by the M, so I'll put F over M. The other equation is the same as it was before. The force, our external force, I applied it to mass A. It's not applied to mass B, so it doesn't enter there. Okay. Well, we've solved the normal coordinate problem. The normal coordinates haven't changed. The oscillator still has the same natural frequencies and the same normal modes. So let's just do that again. I can invert this. I want to transform these x's to u's. There are many ways you could do this, but brute force, I could just, there's lots of ways of doing algebra. So I plug those in and get an equation in the u's. And so what do I get? U1 double dot plus U2 double dot. So after a while of doing this, you'll find shortcuts. But let me just write it all out. I've multiplied through by a square root of 2. So that appears over there. U2 double dot minus U1 double dot plus G over L U2 minus U1 minus 2K over M U2 is equal to 0. So I've just substituted in those x in terms of U into my equation. And I get this kind of messy looking thing. But now let me notice there's some kinds of symmetries to this. So let me try adding and subtracting these two equations. I'm going to know what the answer is going to be anyway. So let me try that. So adding. So if I add them, the U1 cancels there, the U1 cancels there, right? And what happens here? The U1 cancels there, the U1. What did I do wrong? Oh, sorry. I needed a U1 down here. That was on the, no, I've forgotten where that came from. So I plug this in for X sub B, so U2 double dot minus U1 double dot G over L, U2 minus U1. Oh, but then I plug this, yeah, okay, so then the U2, when I took the difference between these, the U2 canceled and I was left with the U1. Okay, so I had the U1 here, and so this cancels. Whew. Okay, so that says that U2, if I divide through by 2, U2 double dot plus G over L U2 is equal to square root of 2 over 2 F over M. So that's adding these two equations. And subtracting gives, so now if I subtract them, the U2 is going to cancel there and there, okay? And so I just get U1 double dot plus, I'll have a G over L. Again, I'm dividing through by 2. G over L. And then I have these terms, since I'm subtracting, they have to add them together. So I get plus 2K over M. So it's a 4K over M, but remember I'm dividing by 2. Times U1 is equal to square root of 2 over 2 F over M. So we've completed it. We've done it. We've decoupled the two equations. So we can separately solve these two now, and we know how to do that. Notice that when I did this in terms of the U1 coordinate system, my force appears in both equations. My force is exciting both normal modes. I haven't arranged my force in such a way to only excite one of the normal modes, which I could do, but it'd be more complicated. So this force is going to excite both normal modes, and so what I'm going to get is a superposition of normal modes, which is going to have a fairly complicated kind of time dependence then. It's going to be a sum of a couple of sine waves. Okay, so we'll continue with that next time and see and go on to more masses.